Hello everyone, and welcome to a quick review of solving problems, energy problems, quantitatively without the use of the energy flow diagrams and energy bar graphs. So basically doing this completely mathematically as any AP student should love to do. First of all, a quick little energy summary. Remember that if a system is isolated, which mechanically means no external forces, then energy is conserved, and that means that the total change in internal energy would, of course, be zero. This is, of course, can be equal to the total change in kinetic energy plus the change in gravitational potential energy plus the change in elastic potential energy plus the change in the dissipated energy. Those are all of our mechanical energy storage mechanisms. And this, of course, is what we call the law of conservation of energy. So here's the law in words, and here it is in math. Now, on the other hand, if we have an external force so that it is not isolated, then work is done by that external force. Work being the transfer of energy into or out of a system by means of that external force. And therefore, the total change in internal energy would no longer be zero, because now there's energy being transferred in or out. How much does that total internal energy change? Well, of course, by the amount of energy that's transferred in or out, otherwise known as work. And again, we could write that change in internal energy as the sum of all of the changes up or down in all of our energy storage mechanisms. This is technically the first law of thermodynamics with the mechanics only version. In the true first law of thermodynamics, there's more than one way of transferring energy. There's also heating and radiation. But we're just doing the mechanical part, of course. So all of our mathematical problems will start with one of these statements. And so we have to decide, is it isolated or not? And therefore, we would know whether energy is conserved, and we would know whether the change in internal energy is equal to zero or the work. So here's one of two quick examples. Here we have a box which is against a compressed spring, which is going to push it, and it'll go around the loop. And here's all the information we know, and hopefully you know what all the variables mean. So first off, we want to find out how fast the box is moving at the top of the frictionless loop. So this is one of those problems where we're only using conservative forces. Right? If you remember, conservative forces are ones that conserve energy, ones that are path independent. So it doesn't matter how we get from here to here, only that this is where we're starting and this is where we're ending. And this allows us to solve with energy much more exotic problems than we do if we have to deal with path dependent or non-conservative forces like friction. So first of all, let's define a system. I'm going to put in the system basically everything: the box, the track, the spring, the wall, and of course the earth. And if I draw that system boundary in as our dotted line, everything that is exerting forces is inside of the system, and therefore the system is isolated and energy is conserved. So from a mathematical standpoint, the total change in the internal energy is zero. Now, we don't have to write out all of the changes in the internal energy. We can just write out the ones that occur here. Kinetic energy changes because it's not moving here and it is moving there. Gravitational potential energy changes because it's changing height. And elastic potential energy changes because the spring is going to uncompress. There is, however, not a change in dissipated energy because there's no friction. So our total change in EK plus our change in EG plus our change in EG has to equal zero. Hopefully you remember that to find the change in a quantity, you have to do the final minus the initial. And it's very important that you do it in that order because obviously subtraction is not commutative. So if you don't go in that order, you get weird negative signs thrown in. Now, not all of these things exist. Some of them are zero. The initial kinetic energy is zero because the box starts from rest. It says so right up here. The initial gravitational potential energy is zero because I assume we'll call the ground zero height. And the final elastic potential energy is zero because once the box leaves the spring, it's no longer compressed. So all three of those cancel, making our math much easier. We're trying to find how fast the box is moving at the top of the frictionless loop, so that's going to be hidden inside of the kinetic energy term. So solving for the kinetic energy, we get that the initial elastic potential energy minus the final gravitational potential energy is equal to the final kinetic. Now this is the stage where you want to look at this equation and make sure everything makes sense. So it's almost as if we are going to do bar graphs and flow diagrams, but kind of in our head. We're starting out, all of the energy is elastic initially. When it gets to the top of the loop, now some of the energy is stored as gravitational, and if you subtract that off, whatever's left over must be kinetic. So hopefully this equation makes sense. If you're good at it, you probably can even skip these first 3 steps, although that might not be a good thing to do given that you sorry about that. Given that you want to show your work, of course, on an AP test. So let's continue on. We're trying to find how fast the box is moving, so we have to multiply by 2 and divide by m. I don't really care how you write this. I personally don't like having fractions, so I try to get rid of the fractions like the 1/2 here. But you can write this really anyway. Take square root of everything. Plug in all of the numbers. Spring constant, how much the spring is compressed, don't forget that's squared, the mass here and here, the gravitational field strength, assuming we're here on the surface of the Earth, and how high it ends up. Plug all that into a calculator and round off to 2 sig figs, and you get a final speed of 2.8 meters per second. So notice here, this would not be a problem we could do with forces and kinematics, because the angles are changing as you go around the loop. That would make it very difficult. But with energy, it's relatively straightforward. So here's example 2. We have a box, 20 kilogram box, pulled from rest 5.0 meters by a 300 Newton applied force. Now, that's not a very exciting kind of problem. And that's because this problem, unlike the last one, has friction. And therefore, we have to deal with the path-dependent non-conservative force. It means we have to know how it gets from point A to point B. And so that makes the problem have to be a little more straightforward so that we can deal with it without using spreadsheets and recursive kind of functions and things like that. So, part A. How much energy is dissipated by friction after the box is pulled 5.0 meters? Well, of course you know that the math model for dissipated energy, and we're talking here about the dissipated energy of surfaces that are rubbing against one another, not air resistance or something like that that's more complex. And so for just surfaces rubbing against one another, the energy dissipated is the force of kinetic friction times the distance. It's the force of kinetic friction, and the d is the distance over which friction acts. Now, of course, we're going to have to first figure out what the force of friction is. So let's draw a quick force diagram. There's our 20 kilogram box. There's, of course, a force of gravity acting down, a support normal force acting up. Those two forces have to cancel because the box is not accelerating up or down. There's an applied force to the right, and then there'll be a force of kinetic friction to the left. Now, since it's starting from rest, it's going to have to accelerate. So this force of kinetic friction is going to have to be smaller than the applied force. How do we calculate that force of kinetic friction? Well, if we remember the math model, it's the coefficient of kinetic friction times the normal force. In this case, the normal force is relatively easy to figure out. Since the net force has to be 0 vertically, the normal force has to balance out the force of gravity, and the force of gravity is mg. Now we could plug numbers in, but of course, this being AP, we want to work symbolically, so we'll plug that in over there, which gives us a force of kinetic friction of mu k mg. Now, remember here, this is not an equation you want to remember because this only is in the case where the normal force balances out the force of gravity. If we were on an incline, or if F of A was being pulled at an angle, the normal force would not be so straightforward to find. Right? So it always can get a little more difficult. Now, we could plug numbers in and get an answer, 68.6 newtons of friction. Notice that's a lot less than the 300 Newton applied force as in the diagram, so the box is accelerating. But I'm going to work symbolically, so I'm going to plug the mu k mg in. And so I get that the amount of energy dissipated is equal to mu k mg times d. Plug in all the numbers, do one calculation. You get about 343 joules, or to 2 sig figs, 340 joules. Now, I want to keep this 343 because I might want to use it later on in the problem. And as some of you have hopefully learned on some of the tests we've done, you need to keep an extra sig fig if you're using part A in later parts. Now, could you do this a lot quicker without writing this all out? Of course you could, but I'm just trying to show you all the steps here. Question B. How fast is the box moving after it's been pulled the 5 meters? The classic question. So, could we do this problem without using energy? Sure. I mean, here we have a force diagram. We could figure out the net force and then the acceleration. Since the forces are constant, the net force is constant, and therefore the acceleration is constant. And uniform accelerations could then be analyzed with kinematic equations. So we certainly could do it as a multi-part problem. This, however, is the energy unit, so we're going to see how we can do it in just one equation, which is actually kind of a quick way and a cool way of doing the problem. On an AP test, they would really let you do it either way. But, you know, asking part A here about energy being dissipated might lead you to try energy. So first, let's define our system as the box, the Earth, right? And that's it. So this is not an isolated system. Something is out here applying that force. Something is interacting with the box that's not part of our system. And therefore, we have a non-isolated system, and energy will not be conserved. Instead, there will be energy transferred in or out of the system by means of that external applied force, otherwise known as work. So, according to the first law of thermodynamics, our change in internal energy in this case is not zero because energy is not conserved. It's equal to the amount of energy transferred in or out, or the amount of work. Initially, the box starts out with no kinetic energy, but then it's moving at the end, so the amount of kinetic energy is changing. It's not changing heights, so no change in EG. There's no spring, so no change in EE. There is, however, friction, and it's being slid across the surface, so there is E dis. So the amount of work is equal to the change in EK plus the change in E dis. Every change in is a final minus an initial. Remember that I tend not to break down the change in E dis. You certainly can if you wish. I choose not to break it down because the initial E dis is always zero because nothing's happened yet. The object hasn't been slid across the table and therefore hasn't dissipated any energy. And so it just gets redundant to break it down. Object starts from rest, so the initial kinetic energy is zero. Trying to find how fast the box is moving, so that's hidden inside of EK. So if we solve here, again, this should be the step that makes sense. Initially, there is no energy in the box Earth system. It's on the ground, there's no springs, it's not moving. So that means the only energy we have at the end is whatever is transferred in. That's the amount of work. If we subtract off the part of the work that's stored as E dis, which of course we already calculated in part A, whatever's left over should be the kinetic energy. Plug in our math models. Now, could you plug in a number right here? Certainly we could. After all, we already did part A. But I'm going to work symbolically because it just looks pretty. Multiply by 2, divide by m, take a square root. Oh, I factored out a d too because there was a d in each term. Do you have to write all these steps? No. Do you have to write it in this form? No. But again, this could be a symbolic problem, so you have to make sure that you plug everything in. The one thing here you might want to look back at, remember work is external force, which is the applied force, times d times the cosine of the angle in between. Since it's being pulled the same direction it's moving, the cosine of theta is the cosine of 0. 5 meters is the distance, 20 kilograms is the mass, 300 newtons is the applied force. The coefficient of kinetic friction between the box and the surface is 0.35, and of course the gravitational field strength near the surface of the Earth, 9.8 newtons per kilogram. You want to have some fun, work through the units, see if they check out, and you get a speed of about 11 meters per second. That's a good 25 miles an hour, so this must be being pulled by something like a car or something like that. Certainly a runner would have a hard time doing that. Now, is this an exhaustive set of examples? No. But the process, really the first 3 or 4 steps, If you can master that, everything after that becomes a matter of equations that we know, math models that we know, and algebra. And so learn the process. Hope you enjoyed the activity.